Welcome to the very first episode of First Principles of Materials Science. It's a brand new podcast series, and we're so excited to take you all on this journey.
Yeah, it's going to be a lot of fun.
Basically, we're going to explore the world of materials,
From the ground up.
starting with the fundamentals, those
Really basic building blocks.
So today we're diving deep into atoms.
You know those tiny,
Yeah, like incredibly tiny.
those little particles that make up, well, pretty much everything.
Everything. I always love to imagine, what's the smallest thing, right? You
Yeah.
think of a grain of sand, a dust mite.
Oh, yeah.
But atoms, prepare to have your mind blown.
Oh, yeah.
Atoms are so small, like a million carbon atoms.
Can fit across the width of a human hair.
A million. It's
Yeah.
crazy. So what exactly are these tiny, tiny things? What are atoms actually made of?
Well, you can kind of imagine it like the miniature solar system. So
Okay.
at the center, you have the nucleus.
Okay.
And that's packed with these positively charged protons
Okay.
and neutral neutrons, so they have no charge. And then whizzing around the nucleus, you have these teeny tiny negatively charged particles.
I love that description. Whizzing around.
Yeah, they're moving, and they're called electrons.
So it's like a tiny bustling city with the nucleus as the downtown and then all this activity in the suburbs, the electrons.
I like that analogy. And here's what's super cool, maybe even cooler. The number of protons in the nucleus determines what element that atom is.
Oh, so if you've got one proton,
That's hydrogen.
okay, if you've got 11 protons,
Of a sodium.
the stuff in table salt.
Exactly. 29 protons, like the pennies in your pocket.
Wow, so just by changing that one number, the number of protons, you get a totally different element. That's incredible.
Yeah.
But how did we figure this all out? Atoms are so tiny. How do you even begin to study something that small?
Well, it's been a journey of scientific discovery
For sure.
for centuries, really.
Yeah.
You know, even the ancient Greeks, they actually had this idea of atomos,
Oh, wow.
meaning uncuttable,
Uncuttable. Okay.
as in the smallest possible particle.
Wow.
But of course, they didn't have the tools to actually, prove it.
Right.
It wasn't until the 19th century that John Dalton
Right.
kind of brought the atom back into the picture.
So he's like the comeback kid of the atom?
Yeah.
Yeah.
Like he was looking at all these chemical reactions and,
cool.
noticing these patterns and piecing together these clues and realizing that matter must be made up of these tiny units.
Like a chemistry Sherlock Holmes.
Yeah, exactly. But even Dalton's model, it was still pretty basic.
Okay.
Then along came J.J. Thomson,
Okay.
and he's the one who discovered the electron,
Oh.
which shook things up, right?
Yeah.
Because suddenly atoms weren't so uncuttable anymore. They had these little pieces inside them.
What was that like for the scientific community? I mean, to suddenly realize that it was even more complex than they initially thought.
Yeah, you can imagine the
Yeah.
excitement, the questions.
Mm.
Because if atoms had these negatively charged particles,
Electrons.
right, well, there had to be something positive to balance it all out.
Oh, of course.
Enter Ernest Rutherford.
Ah, Rutherford, the gold foil experiment.
Yes, the one where he's shooting these particles at a thin sheet of gold,
Yeah.
and some of them bounce back.
Crazy, like shooting bullets at tissue paper and having some of them ricochet.
That's a great way to put it. And that's how he realized, whoa, most of the atom is actually empty space.
Empty space.
Yeah, with just this tiny, dense, positively charged nucleus at the center.
Wow, okay, so we've got Thomson finding the electrons, Rutherford figuring out the nucleus.
Right.
It feels like we're getting closer to understanding the atom.
Yeah, we're building a picture.
But I'm guessing there are still some mysteries to solve.
Oh, yeah, of course. How are those electrons arranged around the nucleus?
Right.
So that's where Niels Bohr comes in,
Oh, okay.
with his model of the atom.
Okay.
And he proposed that electrons actually occupy specific energy levels.
Like what? They can only exist in certain spots.
Yeah, you can almost imagine it like a ladder, right?
Okay.
And those electrons, they can only stand on specific rungs.
Oh, interesting.
And this model, it actually explained why atoms emit specific colors of light when you heat them up.
Oh, wow.
Because those electrons, they're jumping between energy levels
Okay.
and releasing energy as light.
So it all comes down to the electrons, in a way.
In a way, yeah. This was a huge breakthrough. But even Bohr's model,
I have a feeling it didn't explain everything.
it didn't. There were still some things they couldn't quite figure out.
So what happened then? Did scientists just give up? Atoms are too weird.
Not at all. That's where things get even more exciting. They developed a whole new way of thinking about physics at the atomic level. We're talking about quantum mechanics.
That's the one, isn't it? The one where electrons don't actually orbit the nucleus in neat little paths?
Yeah.
But instead, they exist in these fuzzy clouds of probability,
Exactly.
like mind-bending.
It is, but it makes sense when you really start digging into it.
Yeah.
Quantum mechanics is the key to understanding
Okay.
how atoms behave and interact with each other.
Wow, we've gone from ancient Greek philosophers to quantum mechanics. What a journey.
It really shows how far we've come.
And how much we still don't know, probably.
Oh, for sure. This is just the beginning.
Right. So we've covered the basic structure of an atom, its history.
Yeah.
But I want to know more about those subatomic particles themselves.
Okay.
Like protons, neutrons, electrons. Are those smallest things? Or is there like another level?
Well, that's a great question, and I think you're going to be fascinated by the answer.
I am.
Because it turns out protons and neutrons, they aren't truly fundamental particles. Protons and neutrons, they're actually made up of even tinier particles.
Oh, wow, even tinier.
Yeah, and these particles, they're called quarks.
Quarks. That sounds like something out of Star Trek.
It does, doesn't it?
Oh.
But quarks are very real.
Okay.
And there are actually 6 types of quarks.
6.
But only 2 of them.
They are found in atoms.
Okay.
Up quarks and down quarks.
Oh, so those are the ones we're interested in.
Yeah, and it's the combination of these quarks
Okay.
that gives protons and neutrons their properties.
So a proton has, like, a different arrangement of quarks than a neutron.
Exactly.
It's like there's a whole other universe inside each atom.
That's a great way to think about it.
And how are those quarks held together?
Well, they're held together by an incredibly strong force, aptly named the strong force.
Makes sense.
And this force is mediated by particles called gluons.
Gluons. Okay, I'm trying to keep
I know it's a lot of new names.
But it's amazing to think that everything, like literally everything, stars, planets, me, you,
Yeah.
is made up of these tiny, tiny particles interacting in these mind-boggling ways.
It really is mind-boggling when you stop and think about it.
It is. But for now, I think I'm ready to zoom back out a little bit
Okay.
from the realm of quarks and gluons
Yeah.
and talk about the forces happening within the atom itself.
Sounds good. So we've got these negatively charged electrons
Right.
whizzing around a positively charged nucleus.
Yeah.
You'd think they would just like crash into each other.
You would think so. But that's where another fundamental force comes in, the electromagnetic force.
Okay, remind me what that one does.
So the electromagnetic force governs the interactions between charged particles.
Okay.
And in the atom, it creates this delicate balance,
Okay.
keeping the electrons bound to the nucleus,
Okay.
but also preventing them from collapsing into it.
So it's a constant push and pull.
Yeah, exactly, like a delicate dance.
And that's what gives atoms their stability
Right,
and allows them to interact with other atoms.
to form the molecules and materials we see all around us.
Exactly. So speaking of interactions, I want to go back to something we touched on earlier.
Yeah.
The idea that electrons occupy specific energy levels within an atom.
Yeah, good point.
Can you explain that a little more? What does it mean?
Sure. You can kind of think of these energy levels like a set of stairs.
Stairs, okay.
And electrons, they can only exist on those steps.
Not in between.
Nope. And the higher the step, the more energy the electron has.
So they need like a certain amount of energy to climb to a higher step.
That's a good way to think about it. And when an electron absorbs energy, maybe from light or heat,
Okay.
it can jump up to a higher energy level.
And when it loses energy,
It jumps back down,
okay.
releasing that energy as light.
Oh, I see.
And this is why different elements emit different colors of light when they're heated up,
Right.
because their electrons are jumping between different energy levels.
Okay, that makes sense.
Yeah.
But those energy levels, those aren't the only thing affecting how electrons behave, right?
Good catch. You're thinking about electron spin.
Yeah.
So electron spin is a fascinating quantum mechanical property.
It sounds complicated.
It's kind of like an intrinsic angular momentum, almost as if the electron is spinning.
Like a top.
Yeah, but it's not actually spinning in the way we normally think about it.
So it's more of a quantum mechanical spin.
Precisely. And this spin gives the electron a magnetic moment.
Meaning?
It makes it behave like a tiny magnet.
A tiny magnet. Wow. What does that do?
Well, imagine you have a bunch of these tiny electron magnets
Okay.
all interacting with each other.
Okay.
In some materials, like iron, the spins of these electrons can align, creating a macroscopic magnetic field.
Oh, so that's how we get magnets.
Exactly.
Wow, the behavior of these tiny, tiny electron magnets determines whether something is magnetic on a large scale.
That's the amazing thing about this.
Yeah.
Understanding atoms at this tiny scale
Yeah.
gives us insights into the properties of materials.
It's all connected.
It is.
Wow, we've covered so much ground today.
We have.
From the basic structure of an atom
Uh-huh.
to quarks and gluons,
Yeah.
and now quantum spin.
It's been a wild ride.
It has. But now I'm kind of curious about how these atoms actually interact with each other.
To form molecules and materials.
Exactly. Like, how do these tiny Legos build the universe?
Well, that's a great question, and it's what we're going to dive into next. Atoms, they're not just loners. You know, they like to connect.
They're social butterflies.
Yeah. And the way they connect,
Yeah.
well, that determines the properties of the materials they form.
So it's like, it's not just the atoms themselves,
Right.
but how they relate to each other.
Exactly. It's like you can have a pile of bricks,
Yeah.
but it's not a house until you arrange them in a certain way.
Right, right.
Same with atoms. They form bonds with each other,
Oh.
creating molecules and materials.
So let's talk about those bonds.
Okay.
What are the ways atoms can connect?
So one very common type is a covalent bond.
Covalent. Okay.
And in a covalent bond, atoms actually share electrons to fill their outermost energy levels.
So it's like they're both contributing something.
Yeah, you can imagine them holding hands,
Oh.
each contributing an electron to the shared bond.
Okay.
And this creates a really strong bond.
So it's like they're completing each other in a way.
Yeah, and this sharing also, it dictates the arrangement of the atoms.
Okay.
So like, think about water.
Okay.
Each water molecule, H2O,
Right.
it's formed by two hydrogen atoms sharing electrons with an oxygen atom.
So those covalent bonds are what give water its properties.
Exactly. It's amazing how these tiny interactions
Yeah.
lead to, the properties of water that we see.
Exactly. Like it's essential for life.
Yeah, absolutely essential. Okay, another type of bond is an ionic bond.
Ionic. Okay.
So here, instead of sharing,
Okay.
one atom basically donates an electron to another.
So it's more like a give and take.
Exactly. And this creates ions.
Right. One positive, one negative.
Exactly. And then those ions are attracted to each other.
Opposites attract.
Yeah, just like magnets.
Okay. That makes sense.
And this forms a strong bond.
So we've got covalent bonds, sharing ionic bonds, giving and taking.
Yep.
Are there other ways that atoms bond?
Yeah, there's one more really important type. Metallic bonds.
Metallic. Okay.
So in metals, those atoms, they don't hold on to their electrons very tightly.
Oh.
Instead, the electrons are free to roam around.
Free to roam.
Yeah, creating this sea of electrons
Okay.
that holds the metal ions together.
So they're kind of like bouncing around between all the atoms.
Yeah, and this sea of electrons,
Uh-huh.
it explains a lot of the properties we associate with metals.
Like electrical conductivity?
Exactly. Those electrons can move easily,
Yeah.
carrying that electrical current.
And also, I'm guessing, things like malleability, like being able to bend metal,
Exactly.
it's all because of that sea of electrons.
Exactly.
Okay, so we've got covalent, ionic, metallic.
Yep.
Three main ways that atoms bond.
Uh-huh.
And these bonds, they're not just like theoretical concepts, right?
No, they're real.
Scientists can actually study these bonds.
Yeah, you can, using tools like spectroscopy,
Oh, well.
microscopy.
I mean, you can actually see those bonds. I thought they were too small.
Well, not with our naked eyes,
Right.
but we have these sophisticated instruments. Okay.
That let us visualize them indirectly.
Okay.
So like spectroscopy, that allows us to analyze the light that's emitted or absorbed by atoms.
Okay.
And that gives us information about their energy levels, the types of bonds.
It's like atoms have their own fingerprint.
That's a great
And
analogy.
spectroscopy is how we read it.
Exactly. And we have things like scanning, tunneling microscopes,
Okay.
which create images of surfaces at the atomic scale.
So you can actually see the bumps and dips that represent individual atoms.
We can. It's incredible.
It is.
And these tools have been revolutionary
Yeah.
for our understanding of materials.
It feels like we've come such a long way
We have.
from just imagining these tiny uncuttable particles
Right.
to now being able to visualize them and manipulate them.
It's a testament to, our curiosity, our desire to understand the world around us.
Absolutely. I feel like this deep dive has given me a whole new perspective.
Yeah.
Next time I look at a piece of metal, I'm going to be thinking about that sea of electrons.
Or when I drink water, I'm going to be imagining those tiny little bonds.
That's the beauty of understanding atoms.
Yeah,
It changes how you see everything.
it really does. And for our listeners who want to learn even more,
Yeah.
be sure to check out the resources on the Material Science website,
Yes.
the links in the podcast details.
And join us next time
Yeah.
when we explore molecules.
Oh, that'll be fun.
We'll see how these atomic building blocks come together to form even more complex structures.
I'm excited. But until then, keep exploring, keep questioning, and keep marveling at this incredible universe we live in.
And thanks for joining us on this deep dive into atoms.